two satellites are in circular orbits. So let's say this is circular. This is satellite A, has an orbital radius. So this is r of A. Satellite be moved at twice the speed. So if the speed of this is v, then this will be 2v. So they're asking for the orbital radius rb of satellite B. So again, two satellites circular orbit around the same planet. Okay, same planet. And satellite A has an orbital radius of RA, and satellite B moves at twice the speed of satellite A. What is the orbital radius of satellite B? Now we know that AC equals V square by R. The centripetal acceleration equals V square by R. We don't have any information about the masses of them, but mm, but we know that what we do have, we know that the force between the gravitational force between these two planets will be equal to g m over r square. Now this m is the mass for the, okay, so it's m, you could either write as m1 times m2 or capital M for the mass of the planet. Either of them works. And so let's say we do this for planet A. So for planet A, g m, then we have m of A divided by, we have r squared. So this is r of A squared equals to, so this gravitational force provides the centripetal force in this case. That's why we know that F is equals to ma, mass times acceleration, and we have reduced acceleration to be this, so which means this is mv squared by r. So we can equate this thing to m, and since this is satellite A, so it's just v, so v squared by r, which is r of A. Okay, and we do the same thing for satellite B as well. So this will be gm, then we have mb over r square. So r of b squared equals to m, and now for satellite B we have 2m, so m times 2v, sorry, 2v squared upon, we have rb. Now from here what we can do is we can make common things like, oh, so this will be m of b. Yeah, this is m of b and this is m of A, mass of A. Now we can cross out these things from both sides. Okay, same for this one. And we can make gm the subject from here. So if we make gm the subject, we get v squared by ra times ra squared. So we can cut 2ra from 1 like this. So we're left with v squared times ra. So we made this the subject. We multiplied both sides with RA, so you cancel this out. RA got here, squared. Now we know that GM is equals to V squared times RA. As for this one, the same thing. We make GM the subject. So when we distribute square to 2, we get 4 V squared divided by RB multiplied by RB squared. Similarly, we can cut this off and we are left with 4v squared times RB. Now we can equate these two, gm equals gm, so we could say that v squared times ra equals 4v squared times rb. Now they have asked us to find the orbital radius of RA in terms of RA. So we have successfully found a relation between RA and RB in a single equation. And now our job is just make RB the subject. And if we do, so what do we get? V squared times RA divided by 4v squared equals to RB. So v square and v square gets cancelled out. RB equals RA divided by 4. So A is our answer. We can see. There we go. All right, next question. A box of mass m, so because it has a mass m, the gravitational force would be downwards directly, and that would be mg Newton, with g being the gravitational field strength, gravitational attraction, which we take to be 9.8. So 9.8, and a box of mass m is on a frictionless incline, so we don't have any friction, and that makes an angle theta. So if this is theta, so if you observe that this is 90-degree angle and this is theta, so this will be 90 minus theta. So that means if this is 90 minus theta, what do we have? This is again 180 minus 90 minus theta. So it's 180 minus 90 is positive 90 plus theta. Okay, so so if this is the 90 minus theta, this entire thing is also 90, right? So we could say that if this is theta, then this angle here that the weight of this block makes with the vertical axis of the perpendicular axis of this plane is also theta. So a force F is applied to the box parallel to the incline as modeled below. What is the magnitude of the block's acceleration? Now, if we resolve this force, we have one force in this direction to be mg cos theta, and one force in this direction to be mg sine theta, because this is the adjacent one and this is the opposite one. Now both this force F and mg sine theta works or is applied in the same direction. That's why we add them. So this is the resultant force F plus mg sine theta, and we know that resultant force equals to mass times acceleration. They asked for our mass, so we divide this with m to get the acceleration. Now what we can do is, because the answer format is given a different way, we can divide both, v with m and this term with m, so we get f by m plus g sine theta. So that matches our answer C, f by m plus g sine theta. So this will be our answer. There we go. All right. Two boxes are pushed along a floor by force F, as modeled below. The mass of box A is smaller than mass of box A. The boxes move at a constant velocity of 3.5. Okay, constant velocity of 3.5 meters per second to the right. The magnitude of force that box A exerts on B, so A on B, is dash the force B exerts on A. We know that Newton's third law, they must be equal, because it's the same pair force, the same type of force. Hence, we'd say it's equal to. There we go. All right, so one end of an ideal spring is attached to a wall and the other end is attached to a block. As you can see, the block is on a horizontal surface. The spring's equilibrium length L0 is L0. The system is modeled in 4 different configurations below. See the configurations in which the block experiences a rightward spring force. So a rightward spring force. So this is the original length, and if you compress it, it would give a rightward force. This is correct. And as for this one, so L0 equilibrium, the spring's equilibrium length is L0, and this is equilibrium, so you won't give any force at all. This also gives a force at all because you're pushing. The block should be there, but instead you pushed, so it would repel back and give you rightward force. But this one will give you a leftward force because you pulled it. So our answer matches A and B. In this case, we'll have a experience a right. The block would experience a rightward for spring force. There we go. All right. A block A of mass 3m is initially at rest, so equals to 0. On a surface with negligible friction, block B of mass 2m is moving left. So it's moving left when it collides with block A. So here B comes here and it collides with block A. During the collision, block A experiences a net force of magnitude F and okay. So we have a net force on block A, F net A, okay, and experience an acceleration of magnitude a of A, block B experiences a net force of magnitude F net B, and acceleration of magnitude A of B. How do the magnitudes of the net force and acceleration compare to the blocks during the collision? Again, it's the same. These two are the same pair for Newton's third law. The force block A experiences a net force on magnitude, and block B experiences a net force of magnitude. So block F net A is provided by this B, and F net B is provided by this FA. So they will be equal. And because we know that F equals to MA and the mass remains constant surely, but they have different mass. So even if the resultant force is the same, but because they have different mass, they will have different acceleration. If they have the same mass, then we could have selected this. Now the question is, what is that? And we can cancel this too, and we can select B directly because we don't have any other choices. But let's prove that A of B is greater. So in order to do so, let's say I replace both of this with the same variable f because they're equal, right? So for A, we have f equals to 3m times A. So A of A equals f by 3m, or fm times 1 upon 3. For A of B, we have f equals to 2m times A. So A of B would be f by m times half. And you say, which is greater, 0.5 or 0.3? Because 1 by 3 is something like this. Obviously, A of B is greater. And this proves option B. So we can select this safely. There we go. All right, next question. Blocks A and B of masses MA and MB, respectively, are suspended from a string that passes over a pulley. If the mass of block B is greater, so which means this would move downwards and this would move upwards, which expression represents the magnitude of the acceleration of block A. Assume an ideal string and ideal pulley. We know what they mean. So ideal string is just a string. Ideal string has negligible mass and does not stretch when under tension. The tension is the same at all points within the string. An ideal pulley has negligible mass and rotates upon an axis to its center of mass with negligible friction. All right. So because we know that this thing is greater, and here we have the tension, same for this one. If you think that how can they point to the same direction, well, that is not the case. When we observe from the perspective of this object, tension always act outwards. Similarly for A. So when we observe tension from here, it would be upwards. Now down here we have its mass its weight acting, so m of B times g, and here we have m of A times g. Now because it's moving downwards here, so resultant force would in this direction, which means this must be greater. So we write m of b g minus t. So this is the resultant force F equals m of b times the acceleration. They want us to find the magnitude of acceleration of block A. So this is A of B. Okay. Now for A, we have, because it's moving upwards, resultant force is in the upward direction, and hence F equals to ma. This must be greater in order to pull this up. So we write T minus ma of g equals mass m of a times acceleration a of a. Now, because they're connected, you see it connected within a same system. The acceleration of A would equal the acceleration of B. That's why we could just replace it with a single variable. So we'll use just A for here. And because they want us to find an expression, the magnitude of acceleration, we would make T the subject here, MAG plus MA times A, and we have mbg negative mb of a equals t, and we can equate the tension because tension would be the same within the system, and we get m of ag plus m of a equals m of bg minus mb of a. And they want us to find acceleration, so we'll group like terms here. So ma g negative mbg equals, uh, okay, I think if we make this term here would be more suitable. So let's say we have m a times a plus mb of a equal mbg minus mag. We make a the subject from here, a subject from here, so we get ma plus mb equals mbg. We can make g common here, so minus ma. So we have g here. So we have mb minus ma, mb minus ma plus, no, we don't accept, times g, mb minus ma times g, and we have ma plus mb. So this is wrong. We're only left with c. So as you can see, mb minus ma, mb minus ma times g upon we have ma plus mb. So C matches our result. There we go. Next question. We have a block was given an initial push and is now sliding up a rough, which means friction acts opposite to the direction of motion. So F of friction. So four symbols, force of friction, F of F. Okay. Normal direction acts perpendicular to the slide, F on N. And gravity always acts downwards, so this is F of G, which free body diagram models the forces acting on the block. So F cannot, friction cannot act in the same direction as motion. Same for this one. It must act in the direction that I've shown, opposite to the motion. Regarding G, they're labeled correctly, but what about N? Hey, it's parallel. It must be perpendicular to the surface. The surface is inclined or horizontal like this. So our answer is D. There we go. All right. A planet of radius r and mass m has a small moon with an orbital path as shown at the 3 points A, B, and C. A, B, and C. The small moon is at the distance of 1r, 2r, 5r, respectively from the surface of the planet. If it is at a distance of 1r from the surface, then from the center, it would be 2r. Okay, now choose another color, 2r. And for the center, from the center, it would be 3r. And from the center, it would be 6r. And they're asking us to determine the gravitational field strength at point B. Gravitational field strength G equals gm over r square, where m is the mass of the planet. Because gravitational field strength tells you the force you experience per unit mass, so that's why we don't we don't have this m on the numerator. It gets cancelled out, because when we say per unit, we divide with m, and hence this is the formula for g. And they're asking for gb in terms of the gravitational potential at gc. So first we do is we find the gravitational potential at at these both points. So for b, so g of b would be g m, and we divide by, we have 3r here, so 3r squared is basically 9r, so 9r. So this is the gb. For gc we have gm divided by, we have 6r squared, so 6 squared is 36r squared, yeah. So 36 r squared. All right, now they want us to find the value of gb, so we make gb the subject, and we can replace this thing gm by r square from here with 36 gc equals gm r square with this thing. So we get 36 gc divided by 9. This is gb. So 36 divided by 9. So we know that 9 plus 9 is 18. And then 18 times 2 is 36. So 8 is 16 and 36. So it's 4 times. If we cancel this out, it's 4 times. So GB is 4 times then, GC. So our answer is D. There we go. Okay. A pendulum consists of consists of a ball attached to the ceiling by a string. You have tension acting here. Of negligible mass, a ball is released from rest. Okay. At some initial angle from the vertical, as you can see here. This is the angle. And freely swings back and forth in a circular arc. Points A and B lie along this arc as modeled below. As the ball moves from point A to B, what happens to the magnitude of tangential acceleration and centripetal acceleration, as in frictional forces acting on the pendulum are negligible? Now, for the tangential acceleration is provided by, so we have a weight here, mg. Okay. Now, as it moves closer and closer, what happens at this point? At this point, it gets resolved to, if we think about this, it gets resolved to some in this portion and some in this portion, because we have this thing theta. Okay. So what do we have? As we come closer to B, the theta gets reduced. So with the vertical, this is with the vertical. If this is theta, then this is also theta. If this is theta, okay, then this is also theta, because opposite angles. So the one with the opposite to tension is mg cos theta, and the one acting in this direction is mg sine theta. So as we move closer to B, theta gets reduced, and we know that for sine, if theta gets reduced, the sine theta decreases. So the tangential acceleration, okay, so theta is reducing, is getting smaller, coming closer to 0. So the tangential acceleration would actually decrease, yeah, because sine theta decreases, so it decreases. And this explains why it doesn't um just keep on increasing after is increasing the speed after it passes this point. It slows, so it actually the acceleration decreases. And what about centripetal acceleration? Well, the centripetal acceleration is provided by this cos theta, and as theta decreases, cos theta actually increases because cos theta starts from 1 like this. So the cerebral acceleration would actually increase. It won't remain constant. And yeah, centripetal acceleration is provided by the resultant force acting along this radius radical distance here. And mm, cos theta actually, but wait, cos theta actually increases, but resultant force is T minus mg cos theta. So if cos theta increases, the resultant force would actually decrease because F is equals to T minus mg cos theta. So I think that both of them would decrease. Oh, I overthought. Yeah, my first intuition was correct. Outer radical component. Hmm. F cos. So this decreases. Okay. So if it increases, so does T. Okay, the problem with the latter explanation was T doesn't remain constant. I assume T to be constant. So the increase of this G cos theta also, makes F greater, and hence, yeah, the the first explanation was correct. All right. Okay. So the sun has a mass of 1.99 times 10 to the power 30 kg. Saturn has a mass of 5.68 times 10 to the power 26 kg. The average distance from the sun's center to Saturn's center is this. Okay. So we have sun here, and we have Saturn here. Saturn here. And they have asked us to calculate the magnitude of the gravitational force the sun exerts on Saturn when it's an average distance from the sun. So the average distance is this. We know the gravitational force F equals to gmm times r squared. We have a calculator here. We'll use Desmos. So G is given by 6.67 times 10 to the power negative 11. G. Okay. I should have. Yeah. So G times m, mass of the sun, which is 1.99 times 10 to the power 30, times the mass of Saturn, 5.68 times 5.68 times 10 to the power 26, 5.68 times 10 to the power 26 in 1.99 times 10 to the power 30, and the average distance gmm over r squared. So average distance is 1.43 times 10 to the power 12, and we have to square that. All right, it's 10 to the power 22, 3 point something, 10 to the power 22. This is our answer. All right.